And we'll get started on a new chapter. This is going to be, you'll need, if you don't already have a copy, here's the PowerPoints. There, closer, like that. And you'll also want to get a copy of the review document. Like that. Oops. Okay. And the work problems. Like that. Yeah. Now we talk about chemical quantities. That is, unless you have some issues that we need to deal with. If not, we'll proceed. Chapter 9, chemical quantities. Let's see, we're going to cover things like once we balance the equation, which we've learned how to do, what good is it? What do you get out of a balanced equation? And then that will lead us to mole-mole relationships. In other words, when a reaction takes place, it's not the mass that's important. It's the number of atoms and the moles of molecules and atoms that determines the outcome of a reaction. Then we're going to use those relationships to actually determine mass input and output. We already know from Lavoisier, who said that the mass of reactants has to equal the mass of the product. Right? That's true. That's always been true. Always will be true. But once we learn how to use our balanced equation to follow the progress of a reaction, we'll also use that information to calculate the mass of the reactants that go in and the mass of the individual products that come out. And that includes also investigating the concept of limiting reactants, which I'll talk about more later. Okay, so let's move on. Remember, a balanced equation gives us the number of moles of reactant and product. So for instance, if we have methane, I call that a gas, and we combust it, react it with oxygen, we get carbon dioxide, gas, and water. Under standard conditions, water will be a liquid. Okay, so that's not balanced yet, I don't think. We have one carbon, but we got 4 hydrogens. Right? So that gives us 4 oxygens. We need 2 here. Now we're balanced. And what that tells us is one of 2 things. You can look at it 2 different ways. You can look at it as individual atoms and molecules. So 1 molecule of methane reacts with 2 molecules of oxygen and gives us 1 molecule of carbon dioxide and 2 molecules of water. But that doesn't help us very much if we're going to do calculations. The relationship also holds for numbers of moles. In other words, 6.022 times 10 to the 23rd molecules of methane, 1 mole, will react with 2 moles of oxygen and produce 1 mole of carbon dioxide and 2 moles of water. Now that's more useful because when you have that many molecules together in one place, you've usually got enough of them that you can weigh them if you need to, or you can do other calculations with them. But the point is that the ratios here, these coefficients, 1, 2, 1, and 2, tells us the ratio of each of these reactants and products to one another in that chemical reaction. Okay, so here's another one. This particular reaction is ethanol, the drinking kind of alcohol. Ethanol. It can also be burned with oxygen and produces carbon dioxide and water. But notice the ratios are different. 1 molecule of ethanol requires 3 molecules of oxygen as a reactant. And then it will produce 2 molecules of carbon dioxide and 3 molecules of water. Or 1 mole plus 3 moles of oxygen produces 2 moles of carbon dioxide and 3 moles of water. We know it's balanced because we have the same number of atoms of each element on reactants and product side. 2 carbons, 2 carbons. 5 hydrogens, 6 hydrogens actually. 2 times 3 is 6 hydrogens. 6 oxygens, 7 oxygens. Right? So we have 4 and 3 is 7 oxygens. So that equation is balanced. All right. So here's another equation. And this one is written in such a way, notice that this molecule is exactly the same as that one. So we could write this one with just one of those formulas and a 2 in front of it. But the reason it's written that way is because this copper gains electrons and this copper loses electrons. Well, no, that's not true, because they end up in the same place. Oh, I'm sorry. Forget that. My eyes were playing tricks on me. This is copper 1 sulfide. And this is copper 1 oxide. So these are 2 different molecules, but it's unbalanced. So how do we balance it? Well, we could use the budget. Right? If we used our budget procedure, I'm going to leave out the phases here. If we used our budget procedure, right, do that, that, and that, and we have 4 coppers, we have 1 sulfur, and we have 1 oxygen. So that should be 6. 2, 3, 4, 5, 6. And over here we have 1 copper, we have 1 sulfur, and 2 oxygens. So if we put a 4 in front of this one, well, actually, that's not, I'm defying my own rules. We want to keep these separate. Save those to the last. Okay. So let's do oxygen. We have 1 oxygen here, 2 oxygens here, so we need a 2 here, which gives us 2 oxygens, but it also gives us 6 coppers, correct? And we still got 1 sulfur. So now we can balance the copper. So that should balance our equation. All right. So now that we have a balanced equation, what does it mean? What can we do with it? We can look at it several different ways. If we want to answer this particular question, determine how many dozen copper atoms could be produced from a dozen molecules of sulfide and 2 dozen of oxide. Well, if we have a dozen of these, 2 dozen of these, then we could produce 6 dozen coppers and a dozen sulfur dioxide. Right? Our unit of measure here is dozen. And as long as it's a number of something, we can use it. So 1 plus 2 equals 6 plus 1. We can say that in terms of moles also. Right? And we know that we get 6 dozen or 6 moles in the second part, 6 moles of copper from that reaction. Okay, here's another example. Right? We can take water and split it apart into hydrogen and oxygen. All we need is a direct current of electricity, and we can split that molecule and produce these two gases. So what happens? Well, this one splits into 2 hydrogens and 1 oxygen. 2 hydrogens and 1 oxygen. This one splits into 2 hydrogen and 1 oxygen. But the oxygens recombine, as do the hydrogens. Right? And this is the ratio. The point here is the ratio. The ratio here is 2 to 2 to 1. It's the same thing as 4 to 4 to 2. And if we want to, say we have, let's use that example. Say we have this balanced equation with water yielding 2 hydrogens and 1 oxygen. If we say, rather than 2 hydrogens, we have, say, 5 moles of, water, 5 moles of water. Right? How many moles of these products can we produce? We use the coefficients as conversion factors. Right? The ratio is fixed, 2 to 2 to 1. So if we want to cancel moles of water, and produce an answer in terms of moles of hydrogen, our ratio here, what this equation says is that 2 waters equals 2 hydrogens. Remember, conversion factors, if you have an equivalence, you can produce a conversion factor. So for every 2 moles of water, we produce 2 moles of hydrogen. Okay? So this one cancels here. This one is 1 times 5, and we have 5 moles of hydrogen produced for 5 moles of water. Let's see, come on. There we go. So that's what this slide is about, I'm pretty sure. The mole ratio. That's nothing more than a conversion factor. That mole ratio can be used to convert from any number of moles of reactant to product, or go the reverse direction. Right? You can flip that conversion factor over and go backwards from product to reactants and see, well, if I expect to get 5 moles of hydrogen out of this reaction, how many moles of water do I have to start with? And you just work it backwards and you find out your answer. Using these as conversion factors. So we got, how many conversion factors can we make out of this? Well, this one and this one. This one and this one. Or this one and this one. So we have 3 conversion factors in one direction. And we can flip them all 3 over, 3 coming back the direction. So we actually have 6 conversion factors that we can make out of these coefficients, depending on our need. All right. So here's another example. This is sodium silicon fluoride. Okay. A fluoride containing mineral. And what we're going to do with it is combine it with more sodium metal and produce pure silicon plus sodium fluoride. So think about, why would we want to produce pure silicon? Well, I can think of one pretty good example, right? The semiconductor industry lives on pure silicon, right? Computer chips, their base material is silicon, and it has to be absolutely pure. This is a possible way to get it. I don't know if that's how they do it, but you can end up with with pure silicon here. All you have to do now is separate this solid from that solid, which is another problem altogether. Okay, the question in this case is, how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with excess sodium silicon fluoride? So in this case, we're saying that we got plenty of that. Right? It'll never run out. What we're going to do is take 3.5 moles of sodium and use it all up. So if we use that all up, how much sodium fluoride do you get? So what are we headed for? We want to know how much sodium fluoride we can get. We got a balanced equation. We got to be sure that it's balanced. If the equation is not balanced, then you can't go any further. So let's check. 2 sodiums plus 4 is 6 sodiums. 6 sodiums here, that's good. 6 fluorides, yep, 6 fluorides. 1 silicon, and 4 sodiums. Plus 2 sodiums is 6. Okay, so we're good. So now that we've got the balanced equation, we start from 3.5 moles of sodium and create a conversion factor from the balanced equation. Okay? There's our conversion factor. The mole ratio is 6 sodium fluorides for every 4 sodiums. Now, whether you put one on top of the bottom, it's the same as any other dimensional analysis. Which one needs to cancel, which one you want to end up with. We want to cancel moles of sodium, so we put it on the bottom. And moles of sodium fluoride on the top. Cancels these two units of measure. Then now all we have to do is crunch numbers. 6 divided by 4 times 3.5 gives us 5.25 moles of sodium fluoride. So we know that if we take all of this sodium and make sodium fluoride out of it, then if we start with 3.5 moles of sodium, we end up with 5.25 moles of sodium fluoride. All right. Here's another example. Propane. So when we burn propane in our grill or to heat our homes, this is the reaction that takes place. Combine it with oxygen, produce carbon dioxide and water. How many moles of carbon dioxide are formed when 3.74 moles of propane are burned with excess oxygen? And that is the case, right? There's plenty of oxygen in the air. You'll never run out, at least not for that many moles. So we're going to use up all of that propane. Okay. So if we start with 3.74 moles of propane, and we want to convert it to carbon dioxide. And all we need is the correct ratio of those two. So carbon dioxide is here 3, propane is 1. Okay. So these cancel. 3 times that number is what? Let's see. 3 times 4 is 12. Carry the 1. 22. Carry the 2. And 11. Is that one of the answers? Yeah. 11.2 is 2 significant figures. All right. So 11.2 moles of carbon dioxide are produced from our starting amount of 3.74 moles of propane. Okay. Now we want to take that knowledge, that skill of converting moles to moles and use it to find out something that's tangible, right? I don't know how many moles I have in my hand when I'm holding a lump of coal. I don't know how many moles of molecules I have there. But I do know, or I can determine what the mass is. What I want to know is if I start with a certain mass of reactant, how much mass of one of the products do I get? That's more important. That's more tangible. So here's how you do it. You have to start with a balanced equation every time. That's a must. Actually, before the balanced equation, unless you're given the actual formulas for the elements of the molecules, whatever form they take, then you have to be sure those are written correctly also. Then you balance the equation. So actually, there's a step left out here. They're assuming that you have the correct molecules written in proper formula. Now, this is the cardinal rule of doing mass calculations. You have to convert masses to moles. If you don't know moles, you're dead in the water with a balanced equation. If you have so many mass, you have such and such a mass of a reactant, you can't go anywhere in that equation without moles. So you have to convert that to moles. Then you can use the balanced equation to find out the moles of product. Then to get mass, you take that calculated moles and convert it into mass of the product. Okay? That's known as stoichiometry. Oh, did we do that already? Chapter 6. We must have. Okay. So let's use an example. Say we have chromium and oxygen combined to make chromium 3 oxide. So we have chromium solid plus oxygen gas yields chromium 3 oxide. How many grams of chromium 3 oxide can be produced from 15 grams of solid chromium? 15 grams. And we want to know how many grams of this solid can be produced. As long as we have plenty of oxygen, there's no shortage of oxygen. Got all we need. This is excess. Okay? First thing we need to do is balance the equation, correct? So this should be fairly simple. 2 chromiums, 3 oxygens. Okay, we've got an odd number here, an even number here, and an odd there. So there's one trick that I didn't put in that helpful hints that I should have. If you find yourself in this situation where you have no other interfering compounds, oxygen's here and here only, then you can put a 2 in front of this one, makes you 6 oxygens, and a 3 in front of this one makes 6 oxygens. So now the oxygens are balanced. Now all we have to do is balance the chromiums. So that will balance your equation. Now that we've got a balanced equation, we can say, all right, how am I going to get from here to here? Think of it as every time you have a plus sign or an arrow, there's a great wall. You can't get over that wall. You can't go under that wall unless you're moles. If you're moles, then you have a free pass anywhere in that equation. So how do we find moles of chromium? Molar mass. Grams and moles ratio is molar mass. So you have 15 grams of chromium, and you want to convert it to moles, right? So we just need the molar mass of chromium. Look on your periodic table, 52.00 to 2 decimal places, okay? So if we divide 15 by 52, we get, in standard notation, 28846. I'm going to keep all my decimals for now so that there's no rounding error later. So this is moles of chromium. There you go. Now that we have moles, we can use the coefficients as our conversion factor. Right? We want to cancel moles of chromium and determine moles of chromium 3 oxide. All right, what's the ratio? Well, for every 4 chromiums, you get 2 chromium 3 oxide. So essentially, you're taking half of that number. 1, 4, 4, 2, 3. Check my numbers. 28846. 28846. Yeah. This is moles of chromium 3 oxide. Okay. Now, we know how many moles of chromium 3 oxide we get. How many grams do we have? We need another conversion factor. We're going from moles to grams. When you have moles and grams in the same sentence, think molar mass. So what's the molar mass of chromium 3 oxide? Well, we need 2 chromiums, right? We need 2 times 52, and then add to that 3 times oxygen. Okay? So I just say 52, 2 times that, and then 3 times 16 is 48. So I got 152 grams per mole for this compound. So if we want to cancel moles and leave us with grams, this number goes on top. Okay? Then we multiply it by that value. And I get 21.9. Let's see. 3 significant figures. 21.9 grams of chromium 3 oxide. Okay? And these slides are just doing exactly what I did on the board. Let's see. Yep. Equations balanced correctly. 152 grams per mole. Yep. All right. So there's our conversion to moles of chromium. Then we take moles of chromium, find out moles of chromium 3 oxide. And then we convert that moles of chromium trioxide back to mass. Okay. You can do it all in one step, right? Let's do it like that. But I thought it better to break it into pieces so you could understand why we're doing each step. If you know this sequence for that equation, I mean, you could like put it in a Excel spreadsheet and make it do the calculations. If you're going to do this reaction as a chemist over and over and over and over again, then it might be useful to create an Excel spreadsheet with that calculation in it. Then all you have to do is just plug in the values. Because you know the chemistry is right, you know the stoichiometry is right, and when you do your analysis, you just plug in the numbers. All right. Let's see, another example, tin 2 fluoride is added to some dental products to help prevent cavities, right? Another name for that, if you look on a tube of toothpaste that's got fluoride in it, and all of them do now, you will see in the ingredients a compound called stannous fluoride. That's exactly the same thing as tin 2 fluoride. Stannous fluoride is the old name, the one that I had to memorize as a chemistry student. But now with our new convention, we call it tin 2 fluoride, which is probably a better way. But many of the labels on food and drug products use the old convention, because who knows what that means? People have been looking at those things and seeing stannous fluoride for decades. So if you change now, they're going to think, oh, they're putting something new in my product. No, it's the same thing. It's a marketing issue. So tin 2 fluoride is made according to the following reaction. Right? We use tin metal and hydrofluoric acid. And that's the product with an evolution of gas. Hydrogen gas. Okay, that is a balanced equation. 2 hydrogens, 2 fluorides, and 1 tin. So how many grams of tin 2 fluoride can be made from 55 grams of, they should have said hydrofluoric acid here, because that's HF in aqueous solution, and the naming convention is hydrofluoric acid, not hydrogen fluoride. If it were the gas, I mean, if it was a pure hydrogen fluoride, yeah, that's the proper name. But it's not. It's in aqueous solution, so it's hydrofluoric acid. And we've got plenty of tin. There's no shortage of tin. We just use up all of our hydrofluoric acid to produce. And what do we get? Well, we use the procedure as before. And the way I do this is I write out my balanced equation, and then I extract information from the word problem and put it in relationship to the equation. So what are we given? 55 grams of hydrogen fluoride. 55 grams. And the question is, how many grams of tin 2 fluoride can we make? So the question is this one, in grams. Okay, now I know the balanced equation, what's given, and where I'm headed. So I know I have to convert this into moles of that, then convert that moles into this moles, and then convert back into mass. And I think I've got it up here. Yeah, there it is. Now this is a single step. But what we've done is we converted hydrogen fluoride, hydrofluoric acid, into moles of HF. Then we converted the moles of HF by this conversion factor into moles of 10,2-fluoride. And then now that we have moles of 10,2-fluoride, we use the molar mass of that compound to find out the mass, the answer, right there. Okay, and it turns out it's equal to 215 grams. That means if we start off with 55 grams of hydrogen fluoride as the acid, and this reaction will end up with 215 grams of 10,2-fluoride. All right. Oh, another one. In this case, we've got this balanced equation. Phosphorus trichloride in water produces phosphoric acid. Oops. PO3, phosphorus acid. Phosphorus acid and hydrochloric acid. How do I know that they're acids when there's no aqueous marker there? Because there, it's being, this reaction is conducted in aqueous solution. So I know we need to name them as acids. What mass of water is needed to completely react with 20 grams of PCl3? Okay, if we have 20 grams here, we need to convert PCl3 into moles. Then say the ratio here is 1 mole of this for every 3 moles of water. Then we found moles of water, convert it back to mass. Right? And there it is. Convert this to moles, convert moles of PCl3 to moles of water, and then moles of water to mass of water. And that's how much water you need to completely react with 20 grams of phosphorus trichloride in that reaction. All right. Now, up to this point, we've had a known chemicals, known reactants and products in our reaction. Here we have an unknown. Right? This element here is reacted with boron trioxide, diboron trioxide. It produces tetraboron tri-X. We don't know what X is yet, right? And X shows up in 2 different places. But what we want to do is we want to determine what is X. If 175 grams of X reacts with diboron trioxide to produce 2.43 moles of this compound, what's the identity of X? Right? The way you work this type of problem, and it's already balanced for us. Right? So we don't have to worry about that. You're faced with this type of problem. It's good to look at the end of the question and work our way backwards. What's the identity of X? How do you determine the identity of an element? Right? There are 2 ways. If you know the number of protons, if you know the atomic number, it's easy. You just look for the atomic number in the periodic table, and there it is. The question here is, can we get the atomic number out of this information? That was a rhetorical question. The answer is no. There's no way to find out how many protons are here. So our next best option is what's the molar mass of that element, right? Because the periodic table, you'll notice, is from upper left to bottom right, you have an increasing molar mass. And it goes from left to right across the periods, and then you go back, next period, keeps increasing, keeps increasing. So we can use that relationship, an increasing molar mass, to find out what this element is if we know the molar mass, right? So what do we need to determine the molar mass? And I abbreviate that MW for molecular weight. You need to know the mass per moles, right? So if you have a mass of an element, how many moles does that represent? Right? We need those two factors, the mass and the moles that goes with it. Here we have the mass already, 175 grams. What we need is moles. So can we determine the moles of X? Well, let's look at this. We have this relationship, 6X plus 2, B2O3 yields B4X3 plus 3XO2. All right, we're also given 2.43 moles of B4X3. 2.43 moles of this compound. Can we find out the moles of this one from that? I think so. We've been doing it all morning. If you have this many moles, let's do it over here. 2.43 moles of B4X3. We want to cancel B4X3 and leave us with X. And the conversion factor is right here. There's one of those and 6 of these. 1 here, 6 there. So 6 times this, I'm going to use my calculator so I don't make a boo-boo. 2.43 times 6 is 14.58. Of X. Okay? So now we have what we need. So I divide that in 175, and I get 12.0 grams per mole. Now all you have to do is go to your periodic table and follow along and watch the molar masses of the elements increase from left to right and top to bottom. And then when you get to the one that's closest to this one, stop. That's your element. Now there are a couple of places in the periodic table where the molar masses are very close together. And considering experimental error, calculation error, rounding errors, you could be looking at deciding between 2 elements that have nearly the same molar mass. It doesn't happen very often, but when it does, then you need a tiebreaker. But in this case, that is carbon. Okay, there's our conversion, 14.6 moles of X, and there's our molar mass calculation. There's your element. Okay? All right. Let's see what other trouble we can get into here. What do we mean by a stoichiometric mixture? Well, a mixture is two or more components together that retain their identity. So if we mix, I don't know, example. If we mix this element together with that compound, before the reaction takes place, that's a mixture. The stoichiometric mixture is one in which the exact number of moles required of one reaction for reaction with the other one is the proper proportion in which all of the reactants are used up, none left, and they produce all products. That's the stoichiometric mixture. There's no excess, there's nothing limiting in this reaction mixture. They're all used up to produce these products. Okay? And that's determined by the coefficients. So 1 mole of nitrogen in this case reacts with 3 moles of hydrogen. So if you only have 1 mole of nitrogen and 3 moles of hydrogen in that mixture, you have a stoichiometric mixture. You also have one if the ratio is the same. So you have 2 moles of that, 6 moles of that. That's still a stoichiometric mixture because the ratio is exactly the same as the balanced equation. Okay, this is your author's idea of explanation. This one is nitrogen. These are hydrogen, and these are ammonia. In a stoichiometric mixture, you have just exactly the right amount of these reactants, hydrogens and nitrogens, to produce 2 ammonias. And nobody's left out. Everybody's got a dance partner, or 3 or 4, however many, and nobody's left out. Okay? But that's rarely the case. In fact, I don't think there's a single case in the real world where you have a stoichiometric mixture. This is theoretical. The reason being that we can't measure the amount of reactants accurately enough so that we know that there's exactly the right amount. We can get really close sometimes, but never exactly. So whenever you've got 2 or more reactants together before the reaction, and you're told exactly how much of each one there is in that reaction, unless it's identified as a theoretical stoichiometric mixture, then you may assume that one of those reactants runs out and the other one or the others are in excess. There's some of them left over. That's what we mean by limiting reaction mixture. It's not stoichiometric because one of them runs out and the rest are left, a small amount of the others left behind, unreacted. In this case, nitrogen is excess, right? It has no hydrogen to react with these 2. So they're still left over after the reaction. But all the hydrogen is used up. It is the limiting reactant. So once the hydrogen is used up, the reaction stops. Okay. So let's see. There we go. Just what I said, hydrogen runs out first. Nitrogen's in its excess. How do we do these calculations with limiting reactants? You have to find some way to determine which one is limiting. Because like I said, once that limiting reactant runs out, the reaction stops. And that determines the maximum amount of products that can be produced when the limiting reactant is consumed. So here's an example. Methane and water can react under certain conditions and produce hydrogen gas and carbon monoxide. So what do we do first? As always, we make sure that these are written correctly, and they are. We verify that our equation is balanced. 1 carbon, 4, 6 hydrogens, 2 times 3 is 6, and 1 oxygen. That equation is balanced. Okay, so we can proceed. What other information are we given? Wait a minute. Hold on. We're not given any information. We're given the information in a picture. Okay, in this picture, we know that we need 1 methane, which is this one with black. Usually, when we draw pictures, carbon is black, hydrogen's white, oxygen's red. And if you ever play with molecular models, and so you can see how they are arranged in 3 dimensions, the little pieces will be those colors. Carbon's always black, oxygen's always red, hydrogen's always white, and then there are other elements that may be part of that kit will have those colors. So in this case, we need 1, 1 here, 1, 1 there, okay, 1, 1 here, 1, 1 here. Which one's limiting? Water is limiting in this scenario because we have methane, these 2 methanes left over, right? So how much of the products can we produce from this arrangement? Well, if we have 1, 2, 3 moles of this one from that picture, and we have 3 moles of water, that's a stoichiometric amount. But this is not stoichiometric, right? We have extra methane. So we actually have 5 methane. And based on that scenario, this is limiting. Okay, that means this one is excess. Now there's another way. This is by picture. Okay. This is by picture. If we're presented with this information without the pictures, say we say 5 moles here, 3 moles there, how do we determine which one is excess? Well, there are a couple of ways to do it. The way I like the best is to say, assume that all of this is used up. How much hydrogen is produced? How much product is produced? Well, the ratio is 1 to 3. So 3 times as much is produced of this one. So that would produce 9 moles of that product. How about this one? If this one's all used up, it's the same ratio, 1 to 3. So 3 times 5 is 15, right? It would produce 15 moles. Okay? The limiting reactant is the one that produces the least amount of product because it runs out first. So that tells you that this one is limiting. Okay? I like this procedure better because most problems that require a determination of limiting reactant are interested in how much product is produced. So if you do this, not only do you find out which one is limiting, but you find out how much product is produced too. So you've already done that step, and then you just go to finish the answer from there. All right. And these are just the steps in green letters that we just covered. Now, of course, if you're going from mass to mass, then you would have to take the mass and produce moles, mass produce moles, then do this comparison. And then this tells us how many moles of that product. And then you want to know the mass of this product, convert it back. So we're starting to combine skills to answer more interesting questions. Now this one is A's and B's. I don't know why I kept this slide in here. I use A's and B's to represent compounds and elements only when I have to. And I don't think we have to in this case. I think it just muddies the water. So let's continue with, no, sorry, I'm going to skip these. I think it's more instructive to work with real examples. What I need to do is get rid of these slides so I don't have to skip them. All right. Well, let's see. In this case, they're saying that they're actually telling us now that we're assuming that this is carbon. No, that's pay no attention to the man behind the curtain. That's confusing. This just emphasizes the point that you can't just add everything together and determine the outcome of reaction. You got to go through these steps. Right? You've got to determine if you're given exact amounts of reactants, then one of them you can assume is going to run out. And in order to make the calculation, you have to have moles, just like always, moles to go from one side to the other. You have to find out which one runs out first. And that will be the limiting one. Which one produces the least amount of product? Okay. Okay, which of the following mixtures produces the greatest amount of product? This is a good exercise. Okay, hold on a second. All right. So we don't need this up here. We're going to work from the slide. This slide is built to be complete. So first, which reactant is limiting? All right. If you have 2 moles of hydrogen and 2 moles of oxygen, look at it this way. How many moles of oxygen do you need for each 2 moles of hydrogen? You only need 1, correct? So oxygen is excess, and 2 moles of hydrogen is going to produce how many moles of water? Well, 2 to 2, right? So hydrogen is the limiting one. You have an extra mole of oxygen that's not being used. Right? So we produce 2 moles of water, and hydrogen is limited. How about this one? Well, 2 moles of hydrogen only needs 1 mole of oxygen, so we've got excess oxygen again. Only now we've got 2 moles extra of oxygen, but we produce the exact same amount of water, right? Because of the ratio here and here to the product. 2 moles of hydrogen and 1 mole of oxygen, right? Where have we seen this type before? 2 to 1, 2 to 1. That's a stoichiometric mixture. And remember, that's theoretical. Right? In the real world, that never happens. But it would theoretically produce 2 moles of water. How about this one? 3 moles of hydrogen and 1 mole of oxygen. So in this case, which one's limiting? In this case, 1 mole of oxygen needs 2 of hydrogen, and we have excess hydrogen. We'll have an extra mole of hydrogen left over. So oxygen is limiting in this case. And how many does it produce? 1 mole of oxygen produces 2 moles of water. Right? So they all produce the exact same amount of water in each of these cases. All right. Let's see, where am I at? How much time do I have left? We're doing good. All right, I guess I'm going to have to use an A-B here. Simply because I don't think I have any other options. A plus 3B. So this reactant and that reactant are in these ratios, and together they produce 4C. 3 moles of A. So we're going to put that information up here, extract it from the problem, 3 moles of A, react with 6 moles of B, which of the following is true after the reaction is complete? Well, let's see, what do we get? First, let's determine the limiting reactant. If all of this is converted to that, we have 4 times that, correct? 1 to 4. So this would produce 12 moles of C. This one would produce 3 to 4. So what's the conversion factor here? This one we can do in our head. This one we might want to think about. So we need B on the bottom, C on the top. Moles and moles. So C is 4, B is 3. So 3 into 6 is 2, and 2 times 4 is 8. That produces 8 moles of C. This is the limiting one right here. We only get 8 moles out of that reaction. The reaction molar ratio is 1 mole of A to 3 moles of B. That's true. Yeah, that's true. The mixture ratio, 3 moles of A to 6 moles of B. Well, 1 to 3 is the same as, let's see, if this is 3, then 3 times that is 9, so it should be 3 to 9. That one is false. Oh, excuse me. I'm wrong. The actual mixture, that's the molar ratio in the reaction, but the actual mixture is 3 to 6. That's true. So 1 and 2 are both true. B is limiting. Yes, we already determined that. B is limiting, A is in excess. So which one of these is true? A is leftover reactant. Yeah, A is leftover reactant because you only need 2 moles of A and you have 3. Let's see, is that true? If it's 3 to 1, then you need a third of this, 2 moles. That's all you need here, 2 moles of A. That's true. This one is true. A is leftover reactant because for every 1 mole of A, 4 moles of C are produced. For every 1 mole of A is leftover reactant because for every 1 mole of A, 4 moles of C are produced. That's not the reason A is left over. The reason A is left over is because we've got more than we need, not because of this ratio. That ratio would be valid no matter what the amounts were, no matter what the mixture is. So A is not true, but that's not the reason that A is left over. B is left over? No, B is limiting. B runs out, so that can't be true. B is left over? No, that's not true. So A is the one that's true. That's the one that's true. Okay? Now we get a real reaction. We have this reaction, which, by the way, is the Haber process. We take nitrogen from the atmosphere, combine it with hydrogen, and make ammonia. So, how many grams of ammonia can be produced from the mixture of 3 grams each of nitrogen and hydrogen? So we have 3 grams of this, and we have 3 grams of that. There we go. Actually, 2 zeros, right? Okay, so this is given. Is this balanced? We have 6 hydrogens, 2 nitrogen. It's balanced. So we're given exact amounts. That automatically means we've got to find the limiting reactant. So we need to convert this to moles. How do you do that? Molar mass. What's the molar mass of N2? Well, 1 nitrogen is 14.01 grams per mole. So 2 of them are 2802. Right? So that gives us so many moles of nitrogen in the mixture. I get 1.071 times 10 to the minus 1 moles of N2. How about this one? Okay, convert that one to moles of hydrogen. So how many grams per mole of hydrogen, H2? It should be 1.01 times 2, 2.02. So we have 3, and 2.02 divided is 1.485. Yes, hydrogen. Okay, now to find a limiting reactant, you've probably already got it figured out, but we'll be methodical. Convert this to ammonia. Moles of hydrogen, moles of ammonia. What's the ratio? 3 to 2. 3 to 2. So 2/3 of that value is 0.99. 0.99 moles of ammonia. And that's from hydrogen. From nitrogen, we say, convert that to ammonia. So we're going to get rid of nitrogen and leave us with ammonia. And the ratio is 2 to 1. 2 to 1. So 2 times that value is 0.214. 0.214 moles of ammonia. Okay? Compare your numbers. 0.99 versus 0.215. This one produces the least amount. So that means nitrogen is limiting and hydrogen is excess. Now we want to find out how many grams of ammonia. So since this is all that's going to be produced based on the limiting reactant, we just convert that to grams. So we need a conversion factor that will say moles of ammonia and grams. So how many grams of ammonia in a mole? Well, nitrogen is 14.01. And hydrogen, 3 times 1.01 is 3.03. So that's 17.04 times this value, because that's in the numerator, that's in the denominator. And I get 3.65. 3.65 grams of ammonia. Now let's see if we agree here. All right, there's our conversion of nitrogen to moles of nitrogen. Yep. There's our conversion of hydrogen to moles of hydrogen. Now, what they've done here is rather than do it this way, converting to product, they're saying, what's the ratio here? Well, for every one of these, you need 3 of those. So 3 times this is 0.32 or something. 0.32 means you've got plenty of hydrogen. Too much hydrogen. That means this is limiting. Okay, so that's the way, that's another way to do it. And in this case, we're going to take that limiting reactant, convert it to moles of ammonia, and convert moles of ammonia to grams. And there you have it, 3.65 grams of ammonia. Either way works. All right, one more concept, percent yield. Now we're moving into the real world. We went from balanced equation to stoichiometry and a stoichiometric mixture. Then we moved to limiting reactants. That's closer to reality. But one more step is required. When a chemical reaction is investigated, is produced, it produces a product, there are steps along the way. And you can calculate using your balanced equation what you expect to obtain as your product in terms of mass. That's with 100% yield. After you've determined the limiting reactant, you know that it's used up. If it's all used up and produces product, that's 100% conversion. But in reality, steps like side reactions, maybe the reaction you think you're getting is not the one that's, there are more than one reaction that's taking place. So it's not producing your product, it's producing something else. So that's one way that you can lose product. It just isn't produced by the reaction you expect. Another way is most products are produced product mixtures. Sometimes they're pure, of course, but when you have to isolate them from their surroundings, you can lose some in the process. Purification step can lose product. Those are two major ways that have to be considered for obtaining how much product you can get from a reaction when you know it's not going to be 100%. Well, the way to express that is percent yield. Right? It's all summed up in one word: efficiency. How efficient is your reaction? Right? Mention theoretical yield. That's what you expect from the stoichiometry of the reaction. But the actual yield is measured as a product of your reaction. How much actual yield do you get from the reaction? And it's always less than the theoretical. So if you take the actual yield, and usually this is expressed in mass, the actual yield, and divided by the theoretical yield times 100, you get percent yield. Okay? You can do this calculation with moles. You can do this calculation if you have, well, I don't know, partial pressures of gases, whatever the case may be. But typically we use mass. So if we have this reaction where A plus 3B equals 2C, and you determine that 8.33 grams of C should be produced, that's 100% yield. But you measure 7.23 grams as the product. Then the percent yield is simply the ratio of those two numbers. Here we go. So you expect this amount, you actually get that amount, and your reaction is 86.8% efficient. That's the percent yield. Actually, in the real world, if you can get that efficiency out of your reaction, you're doing really well. Some are, you're lucky to get 10%, 15% yield. Okay, find the percent yield product if 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen and excess sulfur. Okay, so let's put this equation up here. 2 sulfurs plus 3 oxygens yield 2 sulfur trioxide. What else are we given? 1.5 grams of sulfur trioxide is produced. 1.5 grams is actual yield. That's what it says. 1.5 grams of sulfur trioxide is produced. That's the actual amount. One of the reactants is given as 1 gram of oxygen. Right? And this is excess. We don't even need to know how much that is. All right. So how do we find, what are we looking for? Percent yield? Percent yield. So we need actual divided by theoretical times 100. We have actual. We need theoretical. So to produce the theoretical number, we work from this value. Right? So remember, you can't go from here to there unless you know moles. So we've got to convert moles first. So 1 gram of oxygen, we need to convert to moles of oxygen. And 1 mole of oxygen weighs how much? Well, 16 for each atom, 32 total. Okay, so that value is 1 divided by 32, or 3.125 times 10 to the minus 2. 2. Now we need to convert that to moles of this. SO3, oxygen. The ratio is 3 to 2. So 2/3 of that value will be moles of sulfur trioxide, or 2.08 times 10 to the minus 2. Of sulfur trioxide. Now to find the theoretical or 100% return on this reaction, we got to convert that back to mass. Grams per mole, right? Moles cancel, leaves us with grams. So what's the molar mass of sulfur trioxide? We have to add it together. Mass of sulfur is what? 32.07. And then 3 oxygens, 3 times 16 is 48. So that's 80.07. Times that value. And I get 1.67. 1.67 grams SO3. That's the theoretical amount. So we're told that we actually get 1.5. And the theoretical is 1.67. Okay. And I get 89.9%. $89.8 is probably closest number to that one, with some rounding error. Okay? That's how you do it. Okay. Let's see. Is this the last problem? It should be. Yes. Okay. This is another percent yield problem, but we're going to bring everything together in one problem. So we're starting with this equation. P4 plus 6F2 yields 4 PF3. Okay, that's a balanced equation. The question is, what mass of P4 is needed to produce 85 grams of PF3 if the reaction is 64.9% efficient? Okay, so let's put what we know up there. We want to know the actual mass of P4. The actual mass of P4 that's needed to produce 85 grams of PF3. Actual. Not theoretical, actual. We want to be able to conduct this reaction and end up with this much in our hand. Well, maybe I wouldn't want to put that in my hand, but in a container. And we also know that the reaction is 64.9% efficient. Okay? So how do we approach this problem? Everything that happens in here is theoretical. So what we need is the theoretical amount of that value before we can find out what we need to start with. So how do you do that? Well, you use the equation, right? Actual divided by theoretical times 100 equals percent yield. We know percent yield is 64.9%. All right, what else do we know? We know that we want an actual amount of 85.0. 85.0 grams. And this is theoretical times 100. Okay? So there's our equation with one unknown. This will give us the theoretical amount. Okay? So theoretical is in the denominator over here, which means it needs to come over to the numerator, and this one comes over to the denominator. So we'll have 85 grams divided by 64.9%. This is times 100 equals what? Theoretical. Okay, let's do that calculation. 85 divided by 64.9 times 100 is 130.97. 130.97. Grams of PF3. So this is the value that we use for our stoichiometry. Now we need to convert that to moles. So we need molar mass of PF3. Grams here, moles there. So what's the molar mass of PF3? We have to add it up. Phosphorus, let's look up phosphorus. 30.97. Okay. And 3 fluorines. Let's see, that's probably off the board. Fluorine is 19.00. Right? Add those together. So 30.97 and 19 times 3. Add those together. We get 87.97. $87.97 divided into this value is 1.489. Moles of PF3. Now we want to find out, now that we've got moles, we can use these coefficients to convert to how much of that in moles. So PF3 is here and P4 is there. So what's the ratio? 4 to 1. 4 to 1. So we divide that number by 4 and we get 0.3722. 0.3722 moles of P4. Now that we know how many moles we need to start with, we just convert it to grams. So what was phosphorus again? 30.97 times 4. So we have this value here, 0.3722 moles of P4. We're going to convert that. Excuse me. You see moles on the bottom, grams on the top. Convert like that. So that was 30.97 times 4. Is 123.88. Okay, times that value. And I get 46.1, rounded off to 3 significant figures. Grams of P4. That's what we need to start with. That many grams of P4, excess fluoride, fluorine, to produce an actual amount of 85 grams of product with this efficiency. Okay, there are all your calculations. And we should come up with 46.1 grams. Right? That pulls everything together that we've learned in this chapter so far. In a single problem. Okay? Well, let's see. We're done a little bit early. So any questions? All right, no questions. We're done for today, and next time we meet, let's see what's on the agenda. We'll do a review. Let's see. Yes. Next Tuesday. Next Tuesday, we'll do a review on this material based upon the review document. So we have problems to work in there to gain some skill at chemical quantities. All right. So if there are no issues, no questions, you're free to go.